The logistic equation is a mathematical model commonly used in the study of population dynamics. And in that context, we have a state variable, x of t, which measures the size of a population at time t. This could be density, this could be volume or number of individuals. Okay, so we're going to assume that x denotes size or volume at time t, and now we're gonna this is size of a population. We're gonna consider this ratio, which is equivalent to have x prime divided by x. This ratio is the ratio of rate of change of population size divided by the population size, and has the name of per capita growth rate. And so what we would like to notice is, look, if we assume that that ratio is constant, okay, so let's suppose that this ratio is equal to a constant b, for example. Well, assuming that the per capita growth rate is constant, is equivalent to assume this is something that's if and only if x prime equals b times x, b being a constant, and this implies that we would have an exponentially growing population, something that looks like a e to the b t, right? So t is the independent variable. So assuming that the per capita growth rate is constant is equivalent to assume that the population size is subject to either exponential growth or exponential decay. Now, if we assume that instead of being constant, that ratio is a ratio that actually is a function of the population size, so we can think of this as some function, I don't know, h of x, such that this function is a function that's linear, okay, the ratio being linear, but not in linear function, but actually something that is linearly decreasing with the population size, then we would have this scenario we have right here. And so this would imply that, remember, we're assuming that x prime over x is equal to that ratio, and then this would imply that x prime is equal to x times expression we have there, which we could write as r times quantity 1 minus x over k. And so this is the equation known as the logistic equation, in which there are two parameters here. There are parameter r and the parameter k. The parameter k, you want to think of that as, well, you know, you could think of the maximum number of seats in a classroom or a movie theater, something similar to the maximum allowed, okay? And so here, maximum allowed in terms of resources of a population. So it denotes the size that can be sustained given available space or sunlight or food. So according to the available resources, this carrying capacity is the maximum size, the maximum sustainable size, if you will. And then the other parameter r is known as the intrinsic growth rate. Okay, so if we could ignore this term here, okay, we could just simply drop that out of the equation and leave that as r. So what we have there, if we were going to drop that out, ignore it out of the equation, we'd have something like x prime equals to r times x, where r is a constant. And precisely that constant would be the constant that we would write here, something a, and this would be e to the rt, right? So that constant is precisely the argument of the exponential function if this per capita growth rate were assumed to be constant. Well, in a sense, the solution of the logistic equation has, under certain conditions, has the behavior of an exponentially growing function. We're going to expand on that in a minute or two, but let's just refer to the meaning. This is known as the intrinsic growth rate, and it denotes the attained per capita growth rate in the case in which the population size is so small that limited resources are neglected. So this means that if the population size is so small, then there's actually not an issue of having some kind of restriction or constraints. And when for small sizes of the population, things have a tendency to behave pretty much like an exponentially growing population, where resources are found at large, and the population sustain that exponentially growing pattern. So the logistic equation in this form is autonomous. The right-hand side is something that can be expressed entirely in terms of the state variable. And in fact, we could write this as Rx minus R over K times X squared. In fact, let's write this minus R over K X squared plus Rx. So here, we're assuming that R and K are positive numbers. Excuse me, this is Rx. Then this right-hand side, which we can call f of x, is clearly a concave down, right? It's a parabola that is concave down, okay? And so, in fact, here we have a plot of that scenario. So we have x prime versus x, right? And this is that curve f of x, okay? And so we can establish here, look, there's a couple of regions here. In this region, x prime is positive. That means that x is increasing, right? And for increasing values of x, then that means that in that region, the arrows along the axis, the horizontal axis with the state variable, those arrows are going to be pointing towards the right because x is increasing. But in this other region, we have that x prime is negative, which means decreasing behavior for x, and x here has arrows that are pointing towards that direction. So very importantly, there are actually two values. Here there is this value here is x bar equals k, and this other value here is x bar equals 0. Those are exactly the roots of this concave down parabola. And what we can see is that according to this one-dimensional flow analysis, we would classify the non-zero equilibrium point x bar equals k as a stable equilibrium, while the trivial equilibrium x bar equals 0, this here would be classified as unstable. Okay. So there are two equilibrium points, and remember, we could take the information, the horizontal axis, right? That this information with the arrows, and we can bring that horizontal axis as the vertical axis here, where we have x of t versus t. Those arrows are pointing away from 0, so the arrows are pointing away from 0, and so here we have the arrows pointing away from 0, and they're actually pointing towards the value of k, right? So here there is value of 0, there is k over 2, and then there is k, and we can see that there are different solutions, okay? Different values, not values, different curves. Each of these curves is 1x of t for a specific initial condition. If initial condition is chosen a little below half of k, a little between half of k and k, and a little above k, then we have these different sketches of solutions. Each of those is a solution x of t. They're all converging. What we see there clearly is that the limit of x of t, this is as t goes to infinity, that is k, is equal to k, precisely because this value k is such that is a stable equilibrium. So in summary, this differential equation known as the logistic equation with this form, an initial condition x sub 0 and parameters r and k has a solution that looks like this. And you can compute this solution using separation of variables, and in fact you will have to apply also using that context partial fractions. Okay, but another thing is that once you have this solution, you could compute the limit of x of t as t goes to infinity, and you can confirm what we had derived or concluded with the one-dimensional flow analysis, that k is a horizontal asymptote of x of t, and that's due to the fact that that k as an equilibrium point is a stable equilibrium. So solutions converge to that equilibrium point. An illustration here towards the end of this is, remember, this is this is in reference to that equation x prime equals r x times 1 minus x over k, okay, for some initial condition. And so here the initial condition is said to be almost around 4. The scale on the vertical axis, this is in millions, okay, these are millions, and these are millions of individuals. This is the size of the population of the United States versus time. These are time steps of 10 years. And so these points that appear depicted here as points are observations or measurements, estimates of the population of the United States every 10 years. And it turns out that if you use these values for the parameters r and the parameter k, then you see the solution of that differential equation known as the logistic equation, as that appears displayed here, depicted as a solid curve. And we were going to, if we computed that solution a little longer in time, then we can see how the solution is kind of settling into that value. Here is approximately 360 something, so it's a little above 350 as it appears displayed here. But this is simply displaying real measurements of the population size of the United States provided by the U.S. Census Bureau, also with specific values for the parameters of the logistic equation.